This is FisiCs, my experimental C compiler and developer tool submission. It supports conventional C compilation while adding optional physics-aware units and dimensions, structured diagnostics, memory instrumentation, and IDE integration. I'll begin with the simplest first user path. The package compiler reports its version and help information, compiles hello world, links the executable, and runs the resulting native program. The more distinctive capability is this physics unit layer. This kinematic stepper is a real multi-file example using quantities such as position in meters, velocity in meters per second, acceleration, time, mass, and energy. These are not comments or naming conventions. The compiler attaches dimensional information to the expressions and follows it through semantic analysis. Here, the generated build graph also shows that physics understands the project's separate translation units, their inputs, and the unit metadata associated with the program. The valid version compiles and produces the expected kinematic output. Now, I deliberately load the invalid version. This attempts an operation between incompatible dimensions, for example, adding position directly to acceleration. Ordinary C would treat both values as compatible numeric types, but physics rejects the operation with unit addition mismatch and stops before code generation. This makes a domain error visible at compile time instead of allowing it to become a simulation bug. And here is an example of an actual runtime try of an incompatible unit addition. It shows the error, it shows why it happened, and how we might be able to fix it. The compiler also includes an instrumented memory check lane. This example tracks a small allocation lifecycle through acquisition, use, and release. The clean run finishes with 0 active allocations. I can then run the intentionally leaky fixture where run 1 release is omitted, and the generated report identifies the remaining active allocation. This provides deterministic, machine-readable memory evidence that can also be consumed by the IDE, and allows for safer memory-related code control. Diagnostics and errors are surfaced directly into my IDE as well. In this example, the program references a symbol that has not been correctly declared and initialized. The analysis remains in an error state and identifies the affected source location. Once I add the proper declaration and initialization, I rerun analysis and the diagnostic clears. This demonstrates the complete edit, diagnose, repair, and revalidate loop rather than only showing a static error message. To validate physics beyond small examples, I collaborated iteratively with Codex and GPT 5.6 to build the Stage G operational differential suite. I chose real workflows for my larger codework applications, while Codex helped convert those behaviors into repeatable fixtures, execute comparisons, isolate mismatches, and expand regression coverage. This ray tracing stage tests 4 operational bytes: render request serialization, scene project round trips, asynchronous render handoff, and the top-level render workflow. Each workflow is built through physics and Clang, repeated for determinism, and compared through its traces and generated artifacts. Final ray tracing result is for both pass targets with 0 blockers. Finally, physics is distributed as notarized Apple Silicon package. A user can download it through my ecosystem website or from the immutable GitHub release. In both lanes, the package is verified using SHA-256 before extraction, and the downloaded binary reports the same published version. Judges can therefore test the compiler immediately without rebuilding it from source. To close out, physics combines native compilation, physics-aware semantics, actionable tooling, and differential validation against Clang in one installable developer workflow.